This is Maureen Julian. Welcome to part 2 of chapter 4, 3 dimensions. Here's our horse turning from 2 to 3 dimensions. Oh yes, our seagull also wants to do the same trick. Let's look at an overview of two-dimensional versus three-dimensional. In two-dimensional, we have 17 space groups, and in 3 dimensions, we hop up to 230 space groups, which is all the different ways you can pack in 17 in 2 dimensions, 230 in 3 dimensions. Now we can divide them up into similar type groups. We had 10 point groups. Here in, from chapter 3, we have 32 point groups. We have 4 crystal systems in the 2D, 7 in the 3D, and then we end up with 4 crystal families or 6 crystal families. The other way to look at it is in terms of the Bravais lattices. So we have a way of looking at the space groups subdivided by point groups or subdivided according to lattices. We have 5 Bravais lattices in 2 dimensions, 14 in 3 dimensions. 4 lattice systems in 2 dimensions, 7 lattice systems in 3 dimensions, and finally the crystal family subsumes both of these 2 pathways, and we have 4 in 2 dimensions and 6 in 3 dimensions. The main thing we want to look at in 3 dimensions, and we'll see this down the line, is in the crystal systems, in the point groups, we have the trigonals. And we had that, they were all the point groups that started out, remember, in the Hermann-Morgan notation, with 3 or 3 bar. When we do the lattices, we're going to end up with a rhombohedral lattice. And even though we have 7 lattices, we have a little bit different interpretation here, and we're going to see this rhombohedral a little later on. Okay, so let's start out with the 3-dimensional Bravais lattices. There are 14 of them. We have the cubics. Remember, at the top we looked at them in the point groups, and here we have 3 Bravais lattices. We have the hexagonals. And the hexagonal lattice can be divided into a primitive lattice or a multiple lattice, and that multiple lattice is called the rhombohedral lattice. Then we have the tetrahedral lattices. We have a primitive and a centered tetrahedral lattice. We have the orthorhombic. The orthorhombic comes in all the possibilities, which is primitive, or centered, or on one side, which would be, here it's chosen as the C, or on the 4 sides. Then monoclinics will have 2 possibilities for Bravais lattices, and finally the triclinics will have 3. Now, this class has half of you are in the orthorhombics and half of you are in the monoclinics. So these are the 2 systems I want you to be most alert to. And finally, we have the rhombohedral over here, and you can see they're both hexagonal, and hexagonal primitive is called hexagonal, hexagonal R is called rhombohedral. A little bit confusing, but as long as you know what it is, you can sort it out. Well, now let's classify the space groups. Well, this is a review. Here's our crystal families, and our crystal systems, and our requirements for the system, which is for triclinic, it's the identity, and this is the requirements for the crystal system. Here are the requirements. Here's all the list of crystal groups, point groups, the number of space groups, and the Bravais lattice. And you can see that sums to 6 crystal families, 7 crystal systems, 32 point groups, 230 space groups, and 14 Bravais lattices. Of course, I do not expect you to memorize any of these numbers. We want to get concepts here, not numbers. So we have 2 new operations, remember in 2 dimensions we had one new operation, that was a glide. Well, we have our glide, and the glide will be an improper operation because remember it's associated with the mirror plane. So you have a mirror and then you have some translation. In 2 dimensions we don't have a symmetry operation with translation because in 2 dimensions we're flat in the plane, but in 3 dimensions we can have a screw operation, and we'll look at that in just a moment. It's just what you think it is. Think of a screw going into the wood. Now here's our glide operations. They consist of a mirror and a translation, and here are our glides. You can see we can glide along A, B, or C. We use this dotted line, or if we're in the plane, we have the arrow gives you the direction of the glide. There are other glides, but I think you'll see that if it's in the normal to the plane, you'll see that it's composed of broken lines, and that's all you have to notice. If you are in the parallel to the plane, if the glide is in the plane, then you're going to have some sort of an arrow, and the arrows are going to show you which direction. You'll mainly be seeing the axial glides. Now the screw is a new proper operation, and here is a staircase which exhibits a screw, and here's a beautiful rendering of the DNA by an artist who was also a crystallographer, and he let me take this picture. So we have this rotation plus translation, and the possibilities of the screw operations are 2, 1. So you go rotation about 180 degrees and up a half. With the 3s, you have 2 possibilities. You can go rotation of 120 and up a third, or rotation of 120 and up 2/3. So, and then if you go, say, 3, 3, you're back to just where you started, so you don't have any translation, so that would be a 3. Likewise with the 2, if you go up another half, then you'll be back to where you started. And so the 4s, they go up by 1/4, 2/4 or a half, and 3/4. And the 6, you have 1, 2, 3, 4, 5, and for the 6s, and that gives you all your screw operations. We indicate the screw operation by this little hurricane symbol, as many people like to call it, and you take the 2, 3, and 4, and 6, and you simply put those extra arrows on there. The only thing I want you to be able to recognize, the main thing we'll be recognizing in the orthorhombic and the monoclinic will be this 2, 1. That's going to be the most important one for you. So now we have both symmorphic and non-symmorphic space groups. So you have the 32 point groups, you have 14 Bravais lattices, and when you add them together, we get, and various possible combinations, we're going to get 73 symmorphic space groups, and we've had that in 2 dimensions, and the non-symmorphics. You should be able to recognize from the notation whether you have a symmorphic or a non-symmorphic system. And this is a repeat of that summary slide we showed earlier. So let's say you had the trigonal primitive, so that would be the Bravais lattice for trigonal primitive. The various point groups that would be trigonal would be 3, 3 bar, 3, 2, 3M, and 3 bar M. This is highlighted because it's anhydrous alum. It's also quartz. And then if you want to have the symmorphic space groups, This is they tell you the lattice P, so that means you add P to both of these, so we get P3 and P3 bar. If you're going to add P to the 3, 2, what you're saying is your twofold can go down either the long or the short axis, so we get two different space groups. And we saw this in the 2-dimensionals. And with the 3M, we can put the mirror plane either down the long or the short direction, diagonal, and the same thing with 3 bar. So, and then associated with that, we get the non-symmorphic space groups. You're not at all responsible for knowing how to get them. You just recognize them. Now, how do we recognize them? Well, look at all of the symmorphics. You can see that you have the point groups, 3 bar, 1 and 2 and M, and there's no translation in the symbol. Now, when you come over here, this is a screw, so we have the translations of their non-symmorphic groups. Here we have screws. The 3, 2 makes it a non-symmorphic group. And the C means you have a C glide here. So the mirror plane is given a translation, and so that turns you into a non-symmorphic group. So you should be able to recognize from the symbols. Now we're going to look at 2 detailed examples. One is hexamethylbenzene, which we've worked with before. That's HMB. And we're going to look at anhydrous alum. And we're going to look at caffeine. I'm going to give you this in another way a little bit later. So the first thing is the interpretation of the space groups from the international tables. That's one of the goals of this course, is to be able to interpret the international tables. So this is what the international tables are going to look like. We have the space group always on the upper left. We have the space group number that will go from 1 to 230. We'll have the Schoenflies symbols and the point group, and we'll have the crystal system of triclinic. Then we have the symmetry diagram. In fact, there are 3 of the symmetry diagrams, so looking down each of 3 different directions, and finally the general position diagram. In this particular case, for all of these, you can see that the origin is at 1 bar. Here's a symbol for 1 bar, and there's the origin, there's a symbol, and there's a symbol. And so in the 3 directions, you have this origin there. Then we have the asymmetric unit. Your exercise for this week is going to be to do the asymmetric unit for your crystal. And here they are, just given to you. And these are the symmetry operations. So this says that the identity is always going to be there. That's always going to be 1. And then in this particular case, we have the 1 bar, and it's located at the origin. Okay, so here is we're going to discuss the asymmetric unit, which you'll be doing for your exercise, your take-home part of the quiz next week. And you can see the asymmetric unit was given as X going from, the red is the asymmetric unit. And we don't worry, when we're doing the programs, I don't worry too much about we're looking for the concept here. And the idea is that the asymmetric unit is 1/2 the unit cell. So we'll put the origin here, and then we have 1/2 in X, and 1 in Y and Z. And you're going to see how to do that. I'm going to give you a little video to do this for the program. Okay, and there's the outline, and we simply do the outline. That's the beginning of the outline, and you finish it up. You'll see that in just a moment. And here's our second page of the international tables. We have the general position, and for us, we're going to be putting everything in, all of your X, Y, and Z into this general position. So we'll be putting both the symmetries and this gives you the multiplicity. So this famous multiplicity character is given right here, and all that says is you've got two of them. So you have two coordinates in your general position. The first is the multiplicity. The second one is a letter which just indicates, it's just a naming of this position. And what they do is they always start at the bottom and they go A, B, C, D, E, F, G, H, I. And you'll see that in all the space groups here, they just start at the bottom and list them. And in this particular, and the side symmetry is the symmetry which we won't really discuss that too much in this course, but you can look in the book for discussion of it. Here's the special positions. Again, we'll be concentrating on the general position in this course. Now, these are the two-dimensional projections, and these are very, very important because the two-dimensional projections are your old friends, and in this case, they're P2. The two-dimensional projections are going to be one of the 17 planar groups. And for your monoclinic and orthorhombic space groups that I've chosen for you, you have just that limited set of P1, P2, P2, MM, P2, MG, P2, GG, and CM and C2MM. Those we're just limited to those projections. Now we're going to these on the bottom. We're going to only use this classification of 1, like we did in the two dimensionals, and we're going to, since there's 230 space groups, we're not going to do all 230. Even I don't do all 230. We're going to just do the layer above and the layer below. So the subgroups will be the largest groups below, and the minimal supergroups are going to be the largest groups above. So we're going to be looking at first 1, and then we're going to be looking at these particular groups, and we can put that into a diagram. Now, from the international tables, you can see that the subgroup is going to be P1 bar, number 1, and notice over here on the left we have order, but it's not the order of the space group, because the order of the space group is what? It's infinite, because we have an infinite number of translations. But each space group has an associated point group, and we put the order of the associated point group. So, and that in order to get a finite situation here, we have every space group has an associated point group. There are less point groups than there are space groups. In 3 dimensions, we have 32 point groups and 230 space groups, so they have to share. And in your case, for the orthorhombic and the monoclinics, you'll see a lot of sharing there. So this is one of the diagrams you're actually going to do, and you read it off the international tables. And then we color the different systems. Here's triclinic. Here's the and these both are triclinic. Oh dear, there's a mistake here. This should have been 1, not 1 bar, number 1. Sorry about that. And here we have all of these are monoclinics, and these two are both trigonals. And you can read that right off your point groups, off the international tables. So the space group information plus the crystal information from the literature gives you your structure of the crystal. So we're going to populate the unit cell. So what we do is we populate the asymmetric unit, and then we put this. Then we operate the various symmetry operations. In the case of the horse, we can calculate the horse. Then we put the twofold, and that gives us the whole unit cell, in this case the 2 horses. So what do we need? We need the unit cell, A, B, C, alpha, beta, gamma. Where do you get that? From the CIF file. We need the shape of the horse, which is the fractional coordinates for the asymmetric unit, and we get that from the literature. And we get the symmetries, which take the asymmetric unit to the unit cell. And once we know the space group, we can look that up in the international tables, and that will give us the various symmetries we need. And this information goes into the program and it plots the atom. Then we have to connect the atoms to put in the bonds. And that's the bonds are not there, really. They're sort of in the mind of the observer, and they're very useful. There are ways of looking at the bonds, but in general, they're just actually put in, which is a very important point to know about crystallography. Now here's what the crystal data is going to look like. In the CIF file, you're going to get the name of the chemical formula, the formula weight, or you can calculate it, the crystal system, the Bravais lattice, and the space group. For the lattice constants, we get that from the literature of the particular crystal we're doing, such as anhydrous alum or hexamethylbenzene or benzene or whatever you're doing. And here's the fractional coordinates. They also come from the literature, and you can calculate the volume and the density. Now we populate the unit cell, and that's what it looks like for hexamethylbenzene. We actually put in the information for the 1, 2, 3, 4, 5, 6 atoms of carbon, and then we use the inversion point to create the others. Remember, when you actually did this a long time ago in chapter 2, you noticed that each of these were whatever this XYZ was. When we go through the inversion point, that was X bar, Y bar, Z bar. And what we were doing is we didn't really know anything about symmetry at that point, and now we're going to put that in. So then if you can look down there are 3 different projections. Some of them are orthogonal, some of them you have to do little tricks, but for we're going to have ordinary down various directions. And here's along the C, the 0, 0, 1, and when you do that, you're going to see P2, and we can see these various projections, and the origin remains the same. So here is looking down the C-axis, and remember, this is really a skinny, this whole atom, this whole molecule is in the plane. Oh, and before I do that, I should put in it's P2. P2 you've already done for your homework, so you're going to see that's if there's one twofold, then you have this whole group of 4 independent twofolds, or as it looks in the diagram, 1, 2, 3, 4, 5, 6, 7, 8, 9. And here is the asymmetric unit, which says this twofold is going to, in 2 dimension, is going to take all these and create these ones. So all you have to do is find these ones in the asymmetric unit, and then you can use your symmetries to create the rest. We can also look down the 100. We're looking at a planar molecule, and you can see also you have these same symmetries. You put this symmetry in the center here, and you can see that operates. And if you actually filled this all out, you would see that you have P2, and here's your asymmetric unit. All you have to do is calculate that group, and you can automatically get this group by the twofold. And we have another direction, and that gives you another looking down. The B, the 010, will give you the 3rd projection. Again, it's a plane, and it's P2. So what you'll be doing with your crystal is you'll be assembling it, and then you're going to look down the projections and label them. About some of the information we can get out of here? For example, we can't really put in the bond, but we do know the distance between, say, A and B. Well, if these are 2 carbon atoms and all of these bonds are equal, then we could take this distance here and cut it in half, and that would be the would give me the radius of the say the B and the A. They would be, all of these would be you would get this, and you would get all those dimensions, and when you do that, you see that the atoms within the hexagonal, or the benzene part of the hexamethyl benzene, all have diameter 1.42 angstroms, very close. And then, but if you look at the ones that are stuck out here, they're called the methyl carbons. If you take this bond length and you subtract the 1.42, you're going to get 1.54. So these are actually bigger atoms than the ones in the aliphatic part. So this is the inversion point in here. There's lots of information you can get out of it. We'll quickly look at anhydrous alum and a little bit on caffeine in another medium. Here's the two diagrams, and you can see we have P321. Notice that we have all threefold, twofold, and one. We don't have any mirrors there, so everything is they're all only rotations, so it's only red. There's no change of handedness. These are other axes here. These are twofolds. This is a screw. We'll talk about that a little bit later. Here's the threefolds, and here is the general position diagram, and you can see that these are related by a rotation. Here's this rotation along here, so you have the plus going above the plane going to a minus below the plane, and so this is the way the system will look. You can see the threefold. Here's the threefold right here, and you can clearly see the threefold, the three pluses, and here the three minuses. This is the way it looks in the international tables. We like the colors because it gives you a lot more information. And here's again the information for the P321. It's exactly the same format as we had before. This is the general position, and this is the multiplicity. That's what you want to watch for. Okay, and here are the asymmetric unit, and the symmetry operations, and this is a three-dimensional version of the asymmetric unit, similar to what we had in hexamethyl benzene, and that's what you'll be doing for your crystal. And in your case, they're going to be parallelograms, or rather parallel pipettes. And parallelogram is 2-dimension, parallel pipette is 3 dimensions. Okay, and here is the same idea for space group 150. You have the max and min of the type 1s, and we can create the tree. The maximal subgroups and minimal subgroups for this group. That's what you'll be doing for yours. And you can see here, if we look at the remember, we're only going to look at type 1 in both cases. This is the minimal, so we have P3. You always go to the ones in the brackets. These ones are sometimes have different relationships here, but this is the general one that is the standardized form. So it's P3, which is space group number 143. So you go P3 number. Oh, that should have been 143. My goodness, we're finding a lot of things here. And you can see that the index is 2, which means that you have the order here is 6, and so you're decreasing it because you're looking at subgroups, so it becomes order 3. All of these ones are looking at the same subgroup, but different sections of it, or different projections, and it's C2, which is C2, which is number 5. And this is monoclinic, and these four are trigonal, and then these are hexagonal. And if you look down here for the supergroups, you see that they all have 2s here, so that means that you go order 6 and go double that 12, so they're all on that level. And you can look here and you can see that number 164 is P3 bar M. So there we go. You'll be asked to create a similar one. Remember, it's always with respect to the group that you're given, the P321. So here that would be with respect to P321. And again, this is the data that you get from the literature, and here's a calculation of a density. So the density is going to be our old friend, mass per unit volume. From the CIF file, you're going to get the C, the Z, you're going to get the formula. You've already calculated it for your own crystal. You've calculated your volume, and you have then Savet, which is Avogadro's number. So here in this case, the volume is the determinant of the G matrix, remember that. And here you can calculate Z to be equal to 1, and we get 1 potassium. We're actually solving for Z in this particular case. You would get it from, you can also get that from the literature. They should all agree. Now, when you assemble the anhydrous alum, you're going to get something like this. So you have, well, it's the same diagram. You're going to have 2 sulfur groups, and you're going to, or you can have sulfur groups, but you can, yeah, these are sulfur groups. And what I'm showing over here on the right is instead of looking at this tetrahedron, we can actually put in the tetrahedron, and you can see how that is organized as the material. So you have this tetrahedron and this tetrahedron, and you can see especially geologists like to put in the tetrahedrons. It's useful to think about things in different ways. So the polyhedral structures are common in many crystals, particularly minerals. And okay, now what we can do is we can not only have we can see that the tetrahedron is slightly distorted. In the regular tetrahedron would have the bonds all equal. You can see there's a difference here. The SiO1, that bond is a little different from these 3. So we don't actually have a tetrahedron in anhydrous atom. You have sort of a squashed tetrahedron. Not squashed by very much, but it does allow you to crystallographically separate out this blue oxygen from the 3 greens. And the same with the angles. The angles would be all perfect, all 109.471 in a perfect tetrahedron, but in this particular case, you can see we have a separation on the left. Now, we also find that there are a lot of crystals that are pretty similar, and so once you find a series, you can get one and then calculate some of the others. Now, for example, on the left is potassium aluminum disulfate, and so the potassiums are the reds, and on the right is the rubidium iron selenate, and we can see that these have a sort of 1-to-1 here, and it doesn't always work out if they are 1-to-1, but they have to be 1-to-1 if they're going to be what we call an isotypic crystal or series. So these are also called isomorphic. They have the same form. So once you understand this one, you can see how you understand the one on the right easily. And if you look at the details of these two, you're going to see they're the same space group, the same Z. You can see that the A and the C are really quite close. They're a little different because they're different materials. The volume is slightly different, And we can see that you have a 1-to-1 substitution, and that goes into these fractional coordinates. The aluminum and the iron are both +3 charge. These are both +1s, so they have to match in that way. And they have similar fractional coordinates. And these fractional coordinates, they're not exact, but they're pretty close, and that's what you're looking for these isotypic series. There's a number, there are many other substances. Here's examples in that isotypic series, and they're all classified as anhydrous alums. There are other compounds of the same form which are not in that form, so you have to be very careful when you're making assignments. Now, there are other famous isotypic series. In fact, this one is probably the most famous of all, and it's the sodium chloride crystal system. And here we have a whole pile of materials that have exactly the same form, the same space group, the same crystal system. The lattice parameters are quite similar, and they have their atomic positions would, in this case, be identical. We can calculate the volume of the asymmetric unit from the volume of the unit cell, and we have to take into consideration both the number of lattice points and the number of operations. You can actually see this when you look at it, and the Z prime gives you the number of molecules in the asymmetric unit. So you take the number of molecules in the whole system, and then you divide it by the multiplicity of the general position, which is n times h, this number of lattice points times the number of operations. So Z and Z prime, let's compare them. They're the number of molecules. Z is the number of molecules in the unit cell, and it's calculated from the density, and it's also sometimes called, that is seen very frequently as N, but in crystallography we always use the Z notation. And then Z prime is the number of molecules or formula units in the asymmetric unit. So we're comparing the whole system plus the asymmetric unit. And remember, what's so important about the asymmetric unit is that's all you have to calculate. You calculate the asymmetric unit, and then you add on the symmetries. So let's look at hexamethylbenzene. That has a multiplicity of 2. You can read that in the international tables. I just showed you where that was. And so we have one molecule here, and Z prime is equal to a half. So all we have to do is calculate half the atoms, and we can use in 3 dimensions the inversion point, or you can use the projections if you want to. Okay, for anhydrous alum, if you look at that, you see you have the 2 sulfates here in the one formula unit. So we only have one formula unit in the whole unit cell, and the multiplicity is 6, so the Z prime would be 1/6. And here's the asymmetric unit in 3 dimensions. Here's an example of caffeine. Here's the whole unit cell. The multiplicity of the general position is 4. You can see you have 4 caffeine molecules and their associated water. And so Z is equal to 4, and Z prime is 1. You can get Z usually from the CIF file, and then to get Z prime, you divide what's in the CIF file by the general position, and here it's 4 by 4, which gives you, divided by 4, which gives you 1. For sodium chloride, that's a little more difficult position. Here, cubic is very difficult to deal with in terms of its symmetry. There are 192 multiplicity of the general position. That's a lot of symmetry elements. So here we have Z equals 4 for sodium chloride. Let's just remind ourselves of that. We have, if we look at the blues, we see we have 1 on each corner, which would be 1/8. So that 1/8 times 8, which gives you 1. And then you have 1 on each of the faces, so you have 6 faces, 1, 2, 3, 4, 5, 6, and each one is a half, so 6. So we have in the interior of the unit cell we have 3, so 3 and 1 is 4, so Z is equal to 4. Then we divide it by the multiplicity and we get 1/48. So it's really just a tiny sliver that keeps multiplying around and around. Aluminum is actually a similar situation here. We have all of them are Z is equal to 4, and then we again for the Z prime is going to be 1/48. In this book we have examples of taken from each of the systems. There's 7 detailed examples. The last one is a cubic one, which is shown here, and you have the multiplicity of the general position. In this particular case is 24. You have 4 atoms in the unit cell, so you have 1/6 or 0.17. That's all, folks. Okay, see you later.